So I'm pretty far through the exams. I'm trying to wait and post announcements or kind of change too much until I have every section kind of graded. That should happen this afternoon. And once I kind of take a look at those, it's looking like the average is probably going to be kind of typically where it is. But if it's a little bit low, there may be a slight curve. If I do something like that, I'll make sure I put an announcement on Canvas. Also, I think I mentioned this last week, I'll be creating like what looks like a new exam, but it's basically just taking your score and making it out of 100. So that original one, because it had 104 points total possible, it's still looking like it's coming up out of 104. I'll get something added in. I'll call the old one like raw exam score, and then kind of the new one exam 1, right? So it'll look and it'll be graded out of 100, and then factor that into your grade. So what I'll start out assuming, because we don't have all the exams in, is that this is everybody's best exam, right? So if you didn't do too well, it's kind of give you kind of maybe a little bit of a scare, kind of need to do better on the next two. If you did really well on the first one, it kind of lets you know, this is going to be weighted the most if you don't do as well on the next two. And so it might look a little bit more rosy if you kind of did well on this one. So I'll have to treat everybody's the same for right now until we actually have more exam scores into where I can kind of weight them differently, okay? Before I forget, I'll also be having an online quiz today. So we've had some time off from that since we've been doing review. There'll be one posted after class that's due before we meet Thursday in class. And then I'll also put up a Learn Smart that needs to be done before we start class on Tuesday, right? A week from today. So you have a week to kind of get on. Should only take about 10 minutes. That shouldn't be too bad, but you have those two things to look forward to, I guess, after class today. Any questions for me before we get kind of started here? We're okay. All right, let me make sure there's nothing in the chat. All right. Okay. So a little bit of what we'll start out with is going to be things that we've already talked about, but a slightly different context. So we left off talking about discrete random variables, right? This is where we could only see integer values. We're now going to think about continuous random variables, right? So this is going to be, we don't know what the outcome of this variable is, but it could take on a bunch of different values. It could take on 1, 5, 9, but it could also be 6.31529, right? It could be any number in between the integers as well. Okay? So, we can think about maybe income where we've got these decimals associated with it, interest rates on loans, or we could see that out to really theoretically whatever decimal we wanted. This is going to be the setup we're thinking about. So it makes life a little bit harder because when we start to think about, just like for the binomial and the Poisson, we had these probability mass functions. Well, essentially, we're going to call it something slightly different. It's the same idea, which is that we're going to have these probability density distributions. The only difference is we can't find the probability of any one value. These probability density functions will only give us the probability over certain intervals. Okay? I'll explain more about this in a second, but once we have the probability density distribution, we could kind of graph this out. Typically we can look at the formulas. They usually look pretty nasty. But we can use that formula. We'll call that f of x, right? That probability density function is some formula. And we'll then use it to graph out the probabilities over different intervals. All right? So, switch over here to the dot cam. Hopefully when she comes back in, she'll shut the door. It's a little bit loud out there. Wait for this to catch up. There we go. So, before we were actually finding the probability x was equal to certain values, right? What's the probability x is equal to 5 successes out of 20, right? Well, now we're going to have this distribution, and just for the sake of giving it some shape, we'll start talking about this a little bit today, but I'll draw a normal distribution because we'll be seeing this a lot. What's going to end up being true is if we wanted to say find the probability from, I don't know, 10 to 15 here, there's some function, right? The way we graphed this line, there was some function f of x with that density distribution where we could plug in different values for x. Kind of think about up here, our y-axis was telling us probabilities, right? So we could plug in all these values for x, get the probability associated with seeing them, and then plot all those y values, right? It's just that when it's not discrete, we've got an infinite number of values technically we'd have to do this for. But the idea is if I could break this up into really small intervals, right? So like really small rectangles here, I could find the area of every single one of these rectangles, right? Or all the probabilities of every different possible outcome. If I add all those rectangles up, that's essentially going to give me the probability I'm between 10 and 15. Right? If I could find those probabilities of these very little intervals, I could do that. Right? So that's kind of the idea behind it. It's not completely theoretically correct in the sense that these little rectangles are very small intervals. What happens if we try to go to where we find the probability of any one value is a little bit different than what we were doing before. So let's think about it this way. Let's say I had a discrete example. We had 4 possible outcomes. They're all equally as likely. What's the probability of any one outcome? Just 1 divided by, 4, right? If we had 4 outcomes. So if we had 100 outcomes, 1 over 100 if they're all equally as likely, n outcomes, 1 over n, right? What happens with a truly continuous variable? The number of outcomes we could see is technically infinite. So 1 over infinity, which in the limit approaches 0. So we have this really weird intuitive concept, which is that the probability of any one value, if there's an infinite number of possible values, the probability of any one value is actually 0. However, the probability that we see outcomes in between 2 values is actually going to be some positive amount. So it's kind of a weird thing. You know, you could think about it though, in our everyday life, if you say, what's the probability? Oh, let me think of one. What's the probability if I choose someone at random? They make exactly $64,132.28. I mean, that probability there, it's not truly continuous in that we have to stop at cents, but essentially it's 0. To get that one value, that's how many other values could we see for income, right? So it's probability is essentially 0. But if I tell you, well, what's the probability somebody makes between 60 and 61,000? Well, it's still going to be probably relatively low just because there's so many other options, but it actually is going to be realistic that I see something in that range. So that's kind of the idea we have here, which is, like I said, it's kind of weird to grasp, but the probability of any one value is 0, but we can find the probability that we're in between 2 values, right? An interval. Okay. So with this in mind, and we'll kind of use this idea a couple times today. Let's see if this switches over. I think I always have to hit this one time when we're doing this. Let's see. Yeah, the first time. There we go. So we've got this probability density function that's going to tell us the probability of seeing that, seeing x take on a value across certain intervals. So the conditions that we need to, are going to come out of this is that, one, it has to be continuous. So we don't see any jumps. So if we think about what I had drawn earlier, it's not like I get to here and all of a sudden the probability jumps up, right? There's going to be this nice kind of smooth continuous line. We also know that if this is giving us probabilities, even if it's over an interval, those probabilities have to at least be 0. And actually, I could even say not only are they greater than or equal to 0, I could actually say that it could never return to me a probability over 1 if I really wanted to get that here. Now, this is kind of similar to something we talked about before, which is that if I integrate that function or look for the area under the curve, right, it's going to be very similar to this idea of discrete random variables, which is if I add up the probability of every possible outcome, those should add up to 1, right? If I add up the probability of every single possible outcome, we said those should add up to 1. Well, really what we're doing here, if I think about integrating this function, really what I could think about is I'm finding every, like one of these small, infinitesimally small intervals, I'd be finding every single one of those rectangles and then adding them all up. Well, that's just like adding up the probabilities of every possible outcome. So when I look for the area under this curve, or I integrate this function from the smallest to the lowest x value, I end up getting that probability essentially of 1, right? Because integrating that function is essentially like adding up the probability of these intervals, right? All these really, really, really small rectangles. Okay? So that's something that we kind of matches with what we talked about with discrete, but it's a little bit trickier. Okay? Any questions up to this point? Should be all right. So, I've already kind of drawn this out for us here, but we can think about this normal distribution. The area under this curve is going to be 1. So knowing that the area under this curve is going to be 1, we can start to do some other things that kind of relate to what we talked about before, but maybe not, don't quite look, or we might not be able to exactly identify that's what they were. So one thing that we've talked about before, not necessarily in the context of a density function, but this idea of making something cumulative, right? So not only do we have this probability density function that gives us the probability, helps us find the probability over certain intervals, we can also have a cumulative density function. We'll call that capital F, right? And now if I plug an x value into this cumulative density function, it gives me the probability I see x, right, or anything below it. Right? So, whoops. If I think about this capital F of x, it's going to use that density function and find me the probability I see that outcome of x or any value below it. Right? So as x gets really close to the largest value we could see, like let's say x was the maximum. If I plug the maximum into my cumulative density function, what should it return to me? If this is telling me probabilities, the probability that I see the maximum value or anything lower than that should just be 1, right? As I get really, really small x values close to the minimum, that cumulative density function is going to get really close to 0. Same idea as when we talked about cumulative relative frequencies and kind of use this idea of being cumulative with discrete random variables as well. So we've kind of already looked over this kind of stuff. But if I think about how I can write this out, so if I wanted the probability that x is less than or equal to a, so I've got some value a, if it helps to think about maybe it's 10 or maybe it's 20, right? If I plotted that against my probability density function, right, this distribution of the outcomes, what I'm really doing is looking for the probability I see a or anything below it, right? Well, once again, I could break this up into like really, really small rectangles. They would all represent the probabilities of these different intervals that are below a. I then could add them all up. So what I'm really looking for is the area under the curve kind of less than a, right? How would I find that? I'd use that cumulative density function. The cumulative density function will essentially start from the minimum, go to that value you're interested in, a, integrate that function, and find you the area underneath it. Right? Now, I'm not going to make you kind of do the integration. We've got some ways that we can kind of sidestep that, but that's the general idea of what that cumulative function is going to do. Okay? We can then think about, well, what if I want to find the probability x is greater than, and I actually have greater than or equal to b here for a reason. So let's say we want the probability x is greater than or equal to b. So what I want really is the area to the right of b, but under that curve. I want to integrate from b to positive infinity or wherever the maximum is. I want to integrate that function and get the area under that curve. Well, how could I do this? Well, if I have that cumulative density function, if I plug b into the cumulative density function, it'll give me the probability that we see x less than or equal to b, right? If I plug b into that cumulative density function, it doesn't give me the probability of being greater than b. It would tell me the probability of being less than b. But if I had that white area, that white kind of shade area, and I know the area under the curve is 1, how could I find the blue shaded area? Yeah, just subtract this area from 1. Right? I know these two components, these two parts have to add up to 1, so it's essentially like using the complement rule. Here's where it gets a little bit tricky. So if I wanted, let me get this paper off. If I wanted to do the probability that x is greater than or equal to b, right? There's a small problem maybe some of you kind of can imagine, or when we're talking about that, or a little confused, right? So let's think about, here's my event a. So I know that this is equal to 1, or that probability is equal to 1 minus a complement. So what would be a complement here? It would be that x is less than b. The issue is, right, if I think about, if I'm trying to use that cumulative density function, that's actually telling me the probability that x is less than or equal to b. Right? So that cumulative density function includes that value of b, but the others, and if it helps, these kind of look like 6s. If it helps to kind of write capital B's, you can there. Just so it doesn't look like we have a number in there. So how do I kind of reconcile that? Well, excuse me. Excuse me. So it's kind of a weird trick. but I can actually just subtract the probability X is equal to B, and I haven't changed anything. Why can I do that and I haven't changed this at all? These two things are equal. Because what's the probability X is equal to B? Probability of any one specific value is, yeah, so it's kind of this weird concept that because we have an infinite number of possible values, the probability of any one value is 0. By subtracting that, I've actually subtracted 0, I haven't changed anything. But now that I have X being less than B and X being equal to B, I could actually write that as probably X is less than or equal to B, which we could just kind of use that cumulative density function to find. Okay? So one thing that's nice with continuous random variables that actually gave us problems with the discrete examples, the equalities essentially don't matter, right? It doesn't matter if I have the equality or not because the probability of any one value is 0. So if I don't have the equality and I say, you know, what's the probability X is less than 10? Well, there I could see 9.9999999 repeated out to infinity, right? So I'm really just, you know, losing out on one specific value, which the probability should be 0. Okay? So it makes life a little bit easier. We don't have to worry as much about these equalities. We're looking at the greater than, kind of less than. Yeah, so we could use that cumulative density function there, and we don't have to worry about that equality being in there. Okay. So what if I wanted the probability I'm in between two values? So let's say I want this light kind of gray shaded area. Well, I can use my cumulative density function to find this as well. Right. So let's switch back here. Also, if it doesn't switch back to the slides and I'm talking and you're like, I don't know, I'm not writing anything down and there's a, let me know because sometimes it hasn't been switching in class here. So, what was I saying? Oh yeah, we want the probability that we're in between two values. So call this A and B. We want the probability that we're in between those values, or the area under the curve in between those two cutoffs. So what we could do is if I plug in to my cumulative density function, that value for A, it's going to return to me the area to the left of A under the curve. Right? If I then plug in B into that cumulative density function, it's going to give me the area under the curve to the left of B. Okay? I've got a bunch of colors going on, but notice if I took that blue area, which is all the area to the left of B, and I subtract the green area, kind of where they overlap, I'd essentially be canceling these out, and I'd be left with just what's in between, which is this black shader, which is what I originally wanted, right? So to find the probability I'm in between two values, I just use the cumulative density function for the larger value and subtract from that the cumulative density function for the smaller value. Okay? And we'll be doing a lot of this once we get to the normal distribution, kind of behind the scenes. Like we're not specifically going to be writing out like in this notation, but we'll be seeing these visuals a lot. So we want to kind of start out building it with this. Okay, any questions on that before we keep moving? All right. I'll leave this up here for a second as I switch back. So we kind of already kind of discussed this. So what if I want, you know, the probability that I'm in between, not the probability I'm in between A and B, but the probability that I'm less than A or greater than B, right? So I want kind of this, I don't know, more bright blue kind of turquoise area. I don't know, turquoise, aqua, whatever you want to call it. Well, if I can find the probability that I'm in between A and B, how could I use this light gray shaded area? Well, the area under the curve is 1. So if I subtract from 1 the probability I'm in between A and B, that would give me the probability that I'm less than or greater than B. Right? So we're really going to be using, you know, drawing these out helps a lot because we're really going to be thinking about we have this area of 1, and sometimes we can break it down into multiple parts. But if I know this part here, this light gray shade area, I automatically know kind of brighter blue area there as well. Right? Just a little bit of simple kind of subtraction from 1. And really, this is underneath this is the complement rule. Okay? So we're going to talk specifically about one type of continuous random variable. And then once we discuss the uniform, we'll then kind of move on to the next one, which will be the normal, spoiler alert. So when we have a uniform distribution, the kind of principle or the identifying factor about that type of a distribution is that every equal sized interval has the same probability of occurring, or is equally as likely. So the probability I see x between 2 and 3 is the same as the probability I see x be between 10 and 11, right? Equal sized intervals there, they would have the same probability. So the density function for that is going to be 1 over the range. So C and D here are really just our minimum and our maximum. So the maximum minus the minimum, that's just our range. And then if we're outside that range, right, if we look at values below the minimum or above the maximum, well, they're just going to have probabilities of occurring of 0, right? This density function is telling us something about the probabilities. So if we want to think about this visually, and I'll try to make this one kind of easy. So let's say I've got a minimum of 10 and a maximum of 20. So we can think about, this is our C and this is our D. Okay? If I think about the very first interval, and let's say I make intervals of size 1. Right? So equal size intervals have to have the same probability of occurring. Remember, kind of what's up here on our y-axis is the probabilities. Right? So if I have another interval of size 1, maybe going from 11 to 12, that has to have the same probability of occurring, so that y-axis point is going to be exactly the same. And then the next interval, 12 to 13, has to be exactly equally as likely. This continues the whole way, so that when we're looking at a uniform distribution, what we really just end up with is kind of this, we call it a curve, but it's really just a flat line, right? Because every equally sized interval here has the same probability of occurring. Okay? Any questions on that before we keep moving? And this one, I think, the reason why I chose intervals of size 1, if I were to use intervals of size 1 here, how many of those intervals would I have in between 10 and 20? Well, the gap in between 10 and 20 is 10, right? I've got a space of like 10. I'm breaking it up into intervals of 1. How many times would 1 go into 10? 10 times. So each one of these intervals of 1, the probability that we would see them occur is 1 over 10, or 1 over the maximum minus the minimum. So 1 over 20 minus 10, or each interval of size 1 has the same likelihood of occurring, which is 1/10, right? They'd be one of the 10 intervals that had width of 1. So that idea is kind of where this density function comes from, right? And that the height of our uniform distribution will just be that density function 1 over the maximum minus the minimum, or 1 over D minus C. Okay, so we can think about every time we see D, we can think about the maximum. C, we can think about the minimum. Okay. Any questions on this before we keep going? We're okay with this? All right, so we can also end up with the density function for being in between two values, right? The probability that x is between A and B, greater than or equal to A, less than or equal to B. So why is this our density function? Okay. Let's go back here. Let me think about the same sort of setup. I'm going to redraw it down here to highlight something. So we had what? 10 to 20, okay? Our height was 1 over D minus C, which ended up being 1/10, right? So let's say I want the probability that I see x be between 12 and 15. So very similar when I was drawing this with the normal distribution curve. It's really just the area under the curve, but between those two values I'm interested in. Our curve is now a flat line, but it's still, we're looking for the area under the curve. So the area under my entire uniform distribution, what should that area be? Yeah, it's just 1, right? If we integrated this function from the lowest to the highest value, we covered every single possible value for x, the area under that curve should be 1. Just now it's not a curve, it's a flat line. Well, here all I have is the area of a rectangle, right? So what would the kind of, depends on how you want to say it. It's like length times width, base times height. Usually we talk about triangles that way, but we think about length times width as being the area of a rectangle, right? So what's the width of my rectangle? Well, it's going from 15 to 12. So that's kind of my width. What's the height? Well, it'd be the height of my uniform distribution, which is just 1/10. But really all that is, right, is what? B minus A and then times 1 over D minus C, which if we simplify this a little bit, we could write like that. And that's where that density function comes from. I personally, you can always use this and plug in the values. I personally think, especially once you've identified the height of the uniform distribution, it's way easier to just think about finding the area of a rectangle, right? If I have the height, it's pretty easy to see what the width is. I typically say the best way to do this is just draw this out and think about you're finding the area of a rectangle. Any questions on that? Okay. All right. So, let me go back to here. So this is kind of our general setup, right? Whenever we're told we have a uniform distribution variable, or sorry, uniformly distributed variable, plot the maximum, plot your minimum, determine what your height is, just 1 over that range. We also can find kind of some summary statistics, or I would say this differently, the summary statistics can help us in some of the other problems, making sure we're not making egregious mistakes. So we have that the mean is simply add up the maximum, the minimum, and divide by 2. So why is that the case? Well, if I think about here, we'll go up to our uniform distribution where we are going from 10 to 20. If I try to exactly split this in half, right, the middle point would be 15, right? What did I do there? I just added up the maximum and the minimum. 10 plus 20 divided by 2 would give me that mean of 15. Okay? So one property of the uniform distribution is it's going to be perfectly symmetric. So the mean actually ends up also being the median. Right? And the reason why is because it's like if we go back to the means we were calculating like day 1, we said another way we could think about those is they were all weighted by 1 over the total number of observations. Right? They were all weighted equally. Well, here, if everything's equally as likely, every value here is weighted the same as every value on the right side of the distribution as well. So everything's going to kind of carry equal weight to the point where our mean is just what exactly splits the minimum and the maximum kind of in 2, right? Or the average of our minimum and our maximum. So that one's easy enough, right? So I'll hold off on that. So just thinking about that mean is equal to the median, right? That's going to be important for something we do here in a second. We also have an equation for the variance. It's not near as intuitive, very similar to the binomial, right? The mean's kind of intuitive, but the variance, we have a mathematical proof to where if we took that density function, right, and we took every value for x and we subtracted this equation for the mean, we squared it, and then multiplied it by that density function, right, or the probability we saw the x value. If we look at that function, right, the variance will always simplify down to this equation right here, which is just the range, right, d minus c, maximum minus the minimum, squared divided by 12. Why that's what it is, that's just what the math simplifies to, right? If we wrote out that formula expression where we plug this in for, we're subtracting the mean, so we're subtracting d plus c over 2, and then we square it and multiply by the density function, it just always simplifies down to this. Any questions on that? Yeah. I mean, you can kind of imagine where the 12 comes from. If I'm subtracting this mean from every single observation, and there's a 2 in there, and then I'm squaring things, and then I go back up here. I think about 1 over d minus c. Oops. And there's a d and a c here. I mean, maybe some things work out to where we, kind of end up getting this thing squared and then multiplied by 2. So that's kind of where it comes from. To follow the steps of exactly how, it's almost like a It's just you're just walking through this mathematical proof where you start out with this expression that you know will equal the variance. It's really complicated. It has the density function. It has the mean equation in there. And then through some simplification, and I say simplification, it's really like applying math rules so that you can simplify it down to this. Yeah. Okay, so here's our variance equation. If we wanted the standard deviation, all we should have to do is take the square root, right? Just like we always do, okay? So that shouldn't be too bad, kind of similar to the binomial in the sense that we have these two equations we know will give us the mean and the variance, and they'll always apply. So let's start working through a couple examples. So let's say I pulled up this movie from my childhood. I used to watch an old Hulk Hogan movie, Mr. Nanny, and they're going to make a second one and bring him back because he's hard up for money. So maybe this movie theater is thinking about how much popcorn to make, and they know that demand typically follows a uniform distribution from anywhere from 1 to 10 pounds. Okay, so we've got this uniformly distributed variable. We write this as with a capital U. We then say, here's the minimum of that uniform, and then here's the maximum. That's how it's written. Okay. So anytime we're writing this out, if we have kind of this, let's try to give you a slightly different look. Okay, so another way that we'll typically be writing these out, here I have some continuous random variable x. It's distributed uniformly. Here's its minimum. Here's its maximum value. Okay? So we were given that it was uniformly distributed with a minimum of 1, maximum of 10. So right away, we could think about, I could draw out the demand for popcorn. And I know it's going to be minimum of 1, maximum of 10. I could then also, if I wanted to, and this will help us kind of in the next question, but what would the height of this distribution be? Well, it's that density function, 1 over the maximum minus the minimum, or 1 over 10 minus 1, or 1/9. But what I wanted was the mean of this distribution. Well, to find the mean, it was just the middle point in between my minimum and my maximum, or add those values up and divide by 2. Right? So the general form was take your maximum plus your minimum, divide by 2. If we do that here, it gives us what? 5.5. So what's going to end up being true is because the mean is equal to the median for a uniform distribution, we say it's symmetric. Right? So if we take that mean, if it's also equal to the median, what percent or what's the proportion or what's the probability that we see a value of 5.5 or greater? The median is the value that exactly splits the data in half such that there is 50% to the right of the median, 50% to the left of the median. Well, here we said the mean is also equal to the median. So we can think about if we were to divide this up, the probability we see something below the mean and the probability we see something above the mean are both 50%, okay? Or probability of area of 0.5. Okay? Any questions on any of this? Shouldn't be too bad yet. So the next question, all right, so we can find the mean here. Now, first of all, hopefully answers like C make no sense for us, right? I mean, we're looking for demand being between 1 and 10. Even if we made a error in our equation, we shouldn't be, 95, we should be able to rule out right away. And, we can think about, here's just kind of a reminder, if we're looking for the probability that we're in between two values, we're really just looking for the area of a rectangle. We already identified the height of our distribution. We said it was 1/9. If you wanted to, you could plug things into our density function. So I'll show it to you both ways. So let's say we're then asked, okay, the theater makes 9.5 pounds. What's the probability that they're going to have angry customers, or essentially that they're not going to be able to meet demand? Well, if remember, demand only goes up to kind of 10 pounds here. If I make 9.5, the only values for which I didn't make enough for are 9.5, 0.00001, 9.5, and anything above that. So what we're thinking about visually here is what's the probability that demand is somewhere in between 9.5, and 10, right? We can't see anything more than 10 because that was the maximum of our distribution. So I really want this area. Well, if I'm looking for the area of that rectangle, what's the width? It goes from 9.5 to 10, right? So 10 minus 9.5. Hold on, I'll do it this way first. So here's our width. We're then going to multiply that by the height of the distribution, which we already determined earlier was 1/9. Right? So I think if we get this entered into our calculator, we'll get about 0.056 there. Now what we could have done is take that density function formula. B is where our interval ends, so it ends at 10. It started at 9.5. And then the maximum and the minimum were just 10 and 1. Okay. Now, if we do this, we get the exact same thing, right? It's just a different way of approaching this. Okay. I said, I technically think it's just easier to find the area of a rectangle, but if we plug the values in, we get the same thing. Okay. Now, if we were looking at this ahead of time, before I'd actually solved for this, what could I have said? I know that the probability of this interval has to be less than a certain value. What value could I have said it was less than? Well, I can definitely say it's less than 1, right? Because the probability I see something from 10, from anywhere between 1 and 10 would be 1. So I know it has to be less than 1. Yeah, I also know it's less than 0.5, right? Because here, the probability that I see the mean or anything up to 10 would be 0.5. So and the mean was 5.5, right? So then the probability I see something above 9.5, well, that's going to have to be something smaller, right? So right away, I know it's going to have to be less than 0.5, simply from this principle that we know that there's 50% to the left and the right of the mean, or probably a 0.5 to the left and right of the mean. Okay, any questions on that one? So I think if we go back, that would have helped me rule out C right away, and then, kind of the other three are viable options there. So a couple things not in the slide I just want to mention. I'm going to try to do different colors when we're talking about these different things, so I don't have to redraw everything. What if I wanted the probability that X, or demand, is between 2 and 2.5 pounds, right? What do I know that probability is going to be right away? Well, definitely less than 0.5, but I can actually say without doing any more additional work, yeah, it's the same probability. It's going to be 0.056. Why? Well, here my interval was of what? Width, or length here of 0.5. This interval is also a width of 0.5. So equally sized width interval has to have the same likelihood of occurring, or the same probability of occurring. Or, think if I plug these in, so now my A and B values are 2.5 and 2. Well, nothing changes in the denominator. The numerator changes, but when I subtract these two things, they both give me 0.5. They're both going to give me the same probability of occurring. Any questions on that before I say the next thing? Okay. What if instead of 2.5, this was 3? What's all you would have to do? If the probability that an interval of size 0.5 happens is 0.056, what's the probability that an interval of size 1 occurs? Yeah, right? Just double that up, right? There's 2 intervals of size 0.5 in an interval of kind of width 1. So if I know the probability that an interval of 0.5 occurs is 0.056, the probability an interval of size 1 would occur would be 2 times that. Right? So it's twice as kind of large. And we could do a couple other things like that, but those are the general rules. Right? Once I can find one of the probability of one of these intervals, it makes finding some of the other ones look a little bit easier. Okay? Any other questions on that before we keep moving? Okay. All right. So this is a great old, I don't know if I'm assuming it was in the 80s, maybe early 90s movie, by the way. All those old Hulk Hogan movies, you should go back and watch and laugh. Like they're supposed to have meanings and things to them, but they're just ultimately funny because of where we were at in the times technological-wise. So I kind of have this as we already did this work, but here is kind of a slide kind of mimicking that as well. So one more kind of take with this example. What would be the probability that if the movie theater makes 9.5 pounds of popcorn, exactly 9.5 pounds of popcorn is demanded, right? So hopefully right away, if you've been listening to what I said, you should know the probability that exactly 9.5 pounds of popcorn is demanded should be what? 0, right? The probability of any one value should be 0. But if we think about this, if I were to take that uniform distribution, going from 10 to 1, and I want the probability of exactly 9.5, if I use that density function and I plug these values in, so my maximum is 10, my minimum is 1. If I'm looking for the probability exactly 9.5, my interval starts and stops at the same point. So this is A and B. 9.5 minus 9.5, well, that's 0. 0 divided by anything is 0. So it doesn't matter what uniform distribution we're looking at, we're always going to have a 0 up here in the numerator when we want to find the probability of exactly one value. And that kind of proves to us what I was saying earlier, at least with this distribution so far. Okay? All right. So just kind of confirms something we had talked about earlier. And once again, you can plug those in that density function, we get 0. So that's the uniform distribution. So are there any questions on that before we kind of move on to the next topic? Moved a little bit quick, so I want to make sure I leave a little bit of time to make sure everybody has a question they can ask it. Okay? So, moving on. There's this guy, Carl Gauss, right? Way back in the day. Really smart guy, kind of, if we look back at those times, anyone who was kind of smart, tended to do a lot of different things, right? So he was involved in mathematics, physics, some astronomy, right? Kind of jack of all trades. But along with another scientist or researcher, who we think about, he came up with the discovery of the normal distribution, right? So the normal distribution is, sometimes it's called the bell curve. Sometimes you might see it called the Gaussian distribution, because this guy helped find, right, come up with or discover it. So it pops up in nature all the time. But, well, before I go on, I'll tell a story about, or supposedly a story about Gauss, kind of interesting. But also just lets us think about how my brain doesn't always work this way, and like pure mathematicians like amaze me. So he got in trouble when he was a kid, supposedly, when they realized he was going to be kind of this genius, that his teacher told him to go over in the corner, count the numbers from 1 to 100, but add them up. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, all the way up to 100, right? She thought, this will keep this little kid busy. He's running around. He's misbehaving. Took him a matter of seconds. He came back. He had an answer for the teacher. She's like, there's no way. She tells him his answer. Sure enough, he's right. And so what he did was he thought about, if I'm trying to add up the numbers from 1 to 100, how much, if I add 1 to 100, I get what? 101. 2 plus 99 is 101. 3 plus 98 is 101. You can do that all the way down to 50 plus 51 is 101. Well, then you essentially have 50 pairs that add up to 101. So 50 times 101, we got 5,050. Right? So this is kind of just like how mathematicians' brains work. It always amazes me that, like, if you asked me to do this right now, I probably wouldn't even think about it that hard. I would probably, it's going to take a while to add up 1 to 100, right? But if we think about these pairs, you go really quickly. And there's actually, his brain was actually able to think of this formula that actually always works, right? So anytime you want to add 1 to up to any number, you can use this equation to figure out what that sum would be, right? So 1 to 200, you would plug 200 in for n, and it would tell you what that would add up to, what that sum would be. Okay? But anyway, so this guy's really smart, right? He discovers the normal distribution or the Gaussian distribution. And we see this pop up all over nature. So I don't know if I'll show them to you today. I might, kind of depending on where we're at towards the end of class. But these things pop up everywhere, right? The normal distribution, if we look at rainfall, let me see, I probably have a couple other examples here. human height, rainfall, temperatures, a lot of human performance. So anytime you look at athletic feats or things like that, if you look at the general population, you see this nice normal distribution. Right? So Gauss, along with this other guy, I would butcher that, de Moivre, right? Probably way off, but they have this book, and it kind of highlights all these different scenarios where they had these recorded rainfall, recorded human height, and they actually found that they all were following this normal distribution, which had this really kind of crazy equation, right? So they discovered that they were all following this probability density function. And don't worry about writing this down. We're not gonna make you use this. We have a way to sidestep this. But really, this gives us the function that we could map out, right? And then think about the area under that curve, right? We could integrate this function from x being equal to 10 to x being equal to 15 and find the area under the curve. Well, this integration is not going to be a lot of fun, right? It's a pretty nasty looking equation, but here's some things to notice. The normal distribution is impacted largely by two things. There's really only two things in this probability density function that make normal distributions vary. One is the mean. The other is going to be the variance, right? Sigma squared here. So the variance will change the shape of this normal distribution, but it'll still be a normal distribution, right? So when I talk about the normal distribution, it's not like it's just one distribution, right? Human height is normally distributed with a much different mean than temperature. Temperature is still a normal distribution, but the means are different. And the variances are also different. So the two things that define our normal distributions are the mean and the variance. These other things, right, we've got that natural number e, and we also have pi in there. So this is kind of these two numbers that really boggle the mind and then kind of pop up in a lot of important places in science and mathematics. Well, sure enough, in the normal distribution, we have both of those. Okay? So we talked about all these things. So here's some characteristics about the normal distribution that we want to keep in mind. For one, it's going to be symmetric. So it's very nice, kind of similar to that uniform distribution. If I look at the mean will be the same as the median, which means that the probability I see something to the left and the right of the mean for a normal distribution is 0.5, right? 0.5 on either side. Okay? I already mentioned it's defined by the mean and the variance, so we're going to change it, and I think we'll talk about today, today or beginning of Thursday, that those two things will kind of influence it. So here, we've got some things. I think I want to draw this out. Well, I'll do this one here, and then I'll draw the next one. So we think about how the mean affects our normal distribution. A really good example of this might be male and female height. If I had a data set of male height and a data set of female height, and then I, turn them into a histogram, what I'll end up seeing is they're both pretty normally distributed. Okay? They both follow a normal distribution, but male height has a slightly higher mean, right? So what that's going to do is it's going to shift that distribution along the x-axis, right? It's going to still be a normal distribution. It's still going to have this kind of bell-shaped curve to it, but it's going to be shifted over so that the mean is maybe a little bit higher here. Or we could think about these are three different countries all having different mean heights, right? But every single person's height in those countries, if we look at Sweden versus choose your countries, they still all follow a normal distribution. Some countries just have a higher average height. Right? Any questions on that? I think we kind of talked about this already a little bit, but we think about the variance, right? I think this one's worth drawing out, seeing me draw it out, but I really want to make sure we have a good grasp on this. And I know I talked about it a little bit before, but let's say I've got this normally distributed variable, right? And here's the mean, right? Let's say its variance is, what's the easier way to do this one? Yeah, so let's say this one has a variance of 100. Now let's say I look at one that has a higher variance. So this distribution, call it distribution 2, let's say it has a variance of 200. With a higher variance, but it has the exact same mean. So let's say group 2's mean is exactly the same as that first group. What's going to end up being true is that with a higher variance, the values further from the mean have a higher probability of occurring than they did before, right? So remember, what's up here on the y-axis is kind of, we can think about as probabilities, right? So with a higher variance, the values further from the mean are more likely to occur, and the values near the mean are less likely to occur, right? There's a wider spread in the data, so it's less likely we see values near the mean, more likely we see values further from the mean, right? So the higher our variance, the flatter this distribution gets, right? Kind of said differently, if I went from a variance of 200 to a variance of 100, right, that variance gets smaller, there's less variation that I can see in these outcomes. Well, then the values near the mean for this blue distribution, I'll use the blue marker to point it out, right? If we had a smaller variance, those probabilities of values near the mean are more likely, right? Or we get this more peaked distribution with a lower variance. Okay? So, you know, we have a higher variance, kind of that leads to a flatter distribution. And then lower variance, kind of a more peaked, right, distribution. Okay. Any questions on that? And then, you know, the difference in means just would shift these distributions, okay? Excuse me. So here's kind of another visualization of that, right? As my variance gets higher, I get flatter and flatter distributions, right? Such that the values near the mean are less likely to occur now. Okay. So if I looked at a distribution like this, what can I say? Two things, right? It looks like male height is pretty normally distributed, and female height looks like it's pretty normally distributed as well, right? Now, what I can see here is if I try to find the mean and the median, right, for both these distributions, it would show me that the mean and the median for male height is a little bit higher than the median and the mean for female height, right? So that shifts that distribution, right? If we're going from kind of females to males. Which of these has a higher variation? Yeah, right? It's kind of hard to see, but if we try to take a look, it looks like there's a wider spread, or it's a flatter, right? It's kind of a shorter or a flatter distribution, which tells us that there's a higher variance. The data is more spread out, right? So, you know, we can tell things like that just by looking at the distributions a lot of the times, right? Whatever the flatter distribution is, it has a higher variance. Now, here's probably a good point to bring this up, because as we start talking about things, you know, I don't know, I'm going to use different groups to look at statistics of, and whenever we compare anything, right, what we're doing is we have an entire distribution, right? So if you just think about the averages here, I just always think that, oh, this overlay is a good, it's a good time to bring this up. So we got a mean for female height, mean for male height, right? I can say that on average, males are taller than females. But what these distributions also show me is, yeah, but look, there's still relatively high probabilities that I see men that are this height, and every single female over here on the female distribution would be taller than those males, right? So just because we have means that shift the distributions, for any one comparison, like any two people we compare, well, this is just 1 point on the distribution, right? So there could be a male, right, that is shorter than a female here, obviously. But when we make the statement, we typically make the statement about the means, right, or the averages, okay? But this is a nice visual for kind of the distributions. Even see, like, when we look at kind of the minimum values for height, right, we have both males and females kind of down there as well. So, okay. So we have this area under the curve, which is 1, right? If I can get this to work here. A couple things that we are gonna, I won't be able to do it today, we're gonna run out of time, but I'll be able to next class, I think, for sure, prove to you why this is the case. But if we go 1 standard deviation below and above the mean, no matter what normally distributed variable we're looking at, right? Rainfall, temperature, human height. If we go 1 standard deviation above and below the mean, there will be 68% of the outcomes will always, or sorry, for the outcomes in that range, we'll see one of them 68% of the time, right? And if we go out to 2, right? So if we think about if I had some normally distributed variable, I use Excel maybe to calculate its mean, calculate its standard deviation. If I went one standard deviation to the left and the right of that mean, 68% of the data would fall within that range. If I go two standard deviations to the left and the right, for a normally distributed variable, if I determine what those values are, I then integrate that probability density function, I find the area under the curve, there will always be 95% of the observations will be in between those two values, or approximately 95%. And then you go 3, you're up to 99%, right? 3 standard deviations. So how do I know this? Or why is this always true? Okay, that's what we're going to be working up to. Right? So we know that the normal distribution is defined by its mean and its variance. So usually what we'll do is we'll write out that we have some random variable x, just like I wrote this earlier, distributed, not uniformly now, but normally. And here's its mean, here's its variance. Right? That's how we're going to be given the information about a variable, or how we would display it. So we have a special case which allows us to simplify that probability density function a little bit. And other people have already done the integration for us. And so let's use their work. Right? Let's be a little bit lazy. So the special case is going to be if we had a standard normally distributed variable, which is a normally distributed variable that has a mean of 0 and a variance of 1. Okay? I mean, you can kind of imagine if I go back, if I have like a mean of 0 and a variance of 1, that kind of simplifies this equation a little bit. It makes it a little bit easier to integrate. So instead of maybe giving someone a stroke scrolling through those so fast, let me do it this way. So we've got this standard normally distributed variable, and this will help us out. Okay? So if I have a mean of 0 and a variance of 1, I can think about when I want to go a certain number of standard deviations away from the mean. If my variance is 1, what's my standard deviation? Yeah, square root of 1 is 1. So when I want to start doing this thing where I was moving a certain number of standard deviations away from the mean, well, really, all I'm doing there is I'm moving a standard deviation is only 1. So going from like 0 to 1 is going 1 standard deviation above the mean, right? Because the mean is 0. Then if I see a value of 2, well, I know that that's 2 standard deviations above the mean. If I see 3.5, well, if the standard deviation is 1, I'm 3.5 standard deviations above the mean. So having this nice kind of standard normal distribution starts to make it easier to think about how many standard deviations above or below the mean I am, because really it's just whatever the number is, right? If the number is 3, I'm 3 standard deviations above. If it's negative 2.5, I'm 2.5 standard deviations below, right? So instead of calling this a random variable x, typically a standard normally distributed variable, how we'll start writing it out is we're going to call these z values, right? I don't honestly know the history behind why they are called z values. I'm guessing it has something to do with we have a 0 mean or kind of a, I don't know. I really am not 100% sure, but that's what we'll typically call them, right? We can, call them anything, I guess, but we typically will reference them as z values. Okay? So if I think about the mean, right? Well, the mean is going to be 0, and then I have this standard deviation of 1, so negative 2. My z value of negative 2 would mean I'm 2 standard deviations below the mean. And then a z value of 1, I'm 1 standard deviation above the mean, so on and so forth. 4.5, I'm 4.5 standard deviations above the mean. The examples would never end, right? So these z values are nice. They have a nice interpretation. But if I start out with a normally distributed variable x, how can I turn that into a standard normally distributed variable, right? So that's what we're going to call z-scores, right? When I convert this variable x into z-scores, those z-scores will be standard normally distributed with a mean of 0 and a variance or a standard deviation of 1. So the way I can do that is just subtract the mean and divide by the standard deviation, right? If I do that, so I take my original variable x, from every single, if I want to think about this as a data set, if I subtracted the mean from every single point in that data set, every single observation, I then divided by the standard deviation, that will give me this z-score. So what will these z-scores be interpreted as? Well, remember, if a z-value is 3, that means it's 3 standard deviations above the mean. So my z-scores then start to be able to be translated to whatever this original x value was, whatever its z-score is, that's how many standard deviations above the mean that x value was. Right? So we're just converting this x value into a z-score to give it an easier interpretation. Okay? So another thing I haven't mentioned, but right, if we've got a negative z-score, that means we're below the mean. Positive z-score means we're above. I've been saying it without explicitly kind of defining that. So we want these z-scores. So I want to show you, I think I'll just do this in Excel because I know I can do it kind of quickly. I think we're running a little bit low on time. Well, not too bad, but I still think it's worth doing this in Excel. Okay, go to view, maybe, there we go. So let's say I try to choose these numbers. What I want. So I've got what? Let's do this, right? So let's say these are my observations, right? So I'm going to find the mean, and then I'm going to find standard deviation of this data set. So here in Excel, right, I can just use the average function to find the mean. Treat this as population data for right now. Kind of next week is going to be when we start to talk about things like sampling. So I find the standard deviation. Right? I've got my mean, I've got my standard deviation. Okay. I always think, you can walk through the mathematical proof of why these z-scores have a mean of 0 and a variance or a standard deviation of 1, but let's just do it with some actual data to prove it to ourselves. So here is my original x variable. In this column, what I'm going to do is I'm going to take that x, oops, if I put an equal sign, this is what I'm going to do. I'll take that x value, I'll subtract the mean, right? And then I'll divide by the standard deviation. So essentially what I'm doing here is I'm creating z-scores. Okay? Now, when I copy this down, I want to keep subtracting the same mean, so I'll freeze that, and dividing by that same cell reference I had the standard deviation. So I'm going to freeze those. Okay? When I drag this down, I'm going to insert a row here just to say I've created z-scores for my original variable x. Okay? And actually, I just want to highlight this. This was the mean of x, and this was the standard deviation of x. Okay? Well, now, what if I want to find the mean of my z-score? Right? And I could also find the standard deviation of my z-score. Right? So that's just find the mean of these z-scores I've created. Right? Hopefully, if I'm not lying to you, this is 0. Okay? So the way that happens is when you subtract the mean from every one of these values, we typically call that, you might see this reference to demeaning, right? It's essentially shifting your normal distribution back towards 0 or forward towards 0, I guess, if you had a negative mean. Right? So by subtracting the mean from every single one of these original x values, I've shifted this data set's distribution to be over at 0. Then by dividing by the standard deviation, if I now look at my new standard deviation of my z-scores, I was telling you these should be 1. Right? So by dividing by the standard deviation, I scaled the data, I scaled the distribution so that I changed the shape of that normal distribution to be exactly the height of a normal distribution that had a variance of 1. So this is, like I said, you can walk through the mathematical proof, but I always think seeing it, just seeing it from the data, this is a lot more meaning, at least for me, it has a little bit more meaning, right? Especially if you don't have a strong math background. So we've got a standard deviation, and it doesn't matter. You might, so the one thing that this depends on is the original variable has to be normally distributed. So that's why I had to create a symmetric distribution. If I made this like, I don't know, 55, notice it doesn't, if I assume it's normally distributed, it doesn't have to start out normally distributed to have the properties of having a mean of 0 and a standard deviation of 1. Now, the z-score distribution here is no longer normally distributed, right? This is not a symmetric distribution. If we look at this, there's way more negative values and there's like one really high value. So if the original variable isn't normally distributed, when I create these z-scores, they may not be normally distributed, but they'll still have a mean of 0 and a standard deviation of 1. But if I start out where it's originally normally distributed, notice the z-scores are also normally distributed there as well. Yeah? Either, yeah, so let me rephrase that. So what I want to highlight here is look at the x variable here. It's normally distributed in the sense that everything that's below and above the mean is kind of like equally as far away. My z-scores end up being that as well, right? It's exactly balanced on both sides. Now, even if it's not, right, and I change this to 55 to where this is no longer a balanced kind of symmetric distribution, notice my mean of the z-scores and the standard deviation of my z-scores is still 0 and 1, but if I'm thinking about what this distribution looks like, it's not normal, right? Now, if I start out with a normal distribution, not only do I know I have a mean of 0 and a variance of 1, but I know that it's also normally distributed, which is what I was trying to do, right? I wasn't just trying to get a mean of 0 and a standard deviation of 1. I was trying to get a normal distribution with a mean of 0 and a variance of 1. So this all starts out assuming that we have a normally distributed variable, right? But the fact that the mean would be 0 and the standard deviation, that holds no matter what. Yep. All right, so I think that's a nice kind of way to depict that. Got a couple more minutes. I'll do one more thing here, I think, and then we'll end it out. So I always like, I stole this from a book, but I like this visual depiction because I'll start doing this a lot as well, where I start out with this original variable x, and then I start mapping out whatever value of x we're looking at, what z-score does that translate to, right? So you can kind of follow, okay, something that's 2 standard deviations above the mean has a z-score of 2. So why do I know that's the case? So, I mean, with the interpretation, I told you that's the interpretation of the z-score. But other than that, like how mathematically, why does that hold? So when I think about my z-scores, I take whatever x value I'm interested in, I subtract the mean and divide by the standard deviation. So let's say the x value I'm interested in is 2 standard deviations above the mean, whatever number that translates to. Well, if I plug that in, right, 2 standard, that's my x value. I subtract the mean, divide by the standard deviation. Well, this cancels, and I'd be left with a z-score of 2. So that's why if we look at an x value, there's a certain number of standard deviations above or below the mean. That's why that interpretation of the z-score holds, right? Because an x value that's 2 standard deviations above the mean, once I plug that into my z-score equation, I would get 2. It's 2 standard deviations above the mean. And I could do this for whatever number of standard deviations I'm interested in, right? And because we can do that, that's why we can map these out, right? Something that's 3 standard deviations below the mean, z-score of -3. Right? So what use are these z-scores? Well, you can imagine if we're trying to find the probability that we're in between 2 values, I don't want to have to integrate that probability mass function between A and B. I don't want to do that. It's a lot of work. It's pretty tough. But we have these pre-built tables that will tell us the probability I'm in between certain z-scores. So if I can convert these values of A and B, right, these might be like 5 and 10. If I can convert those into z-scores, I could then use those z-scores to say, okay, what's the probability I'm in between these 2 z-scores? And someone's already done all that work for us. So I will post after class this file that we will probably be using for a large part of the rest of this semester. And actually, I don't think I have it in the new folder yet. So I'm going to go back and it should be in here somewhere. Got T tables. There they are. I'll be posting this file on Canvas, which I'll explain how we use it kind of more on Thursday. But this is going to be called our standard normal or our Z tables. Right? So once we have these Z values, I can use this table to start to find, well, what's the probability I saw something with this Z value or below. Right? So we'll start working with that, next class. We'll get that up on Canvas. If you want to print it out and have it in front of you, makes it a little bit easier to follow, or make sure you can pull it up on a screen if you're, have your computer in front of you, because to be completely honest, like, this is even zoomed in a little bit. If I zoom in more, then we cut off part of the table, but it's still kind of small. So it might be easier to have it like tactile in front of you or on the screen in front of you if you want that. So I'll get that up on Canvas, as well as the online quiz and that Learn Smart that's due not until next Tuesday's class. Okay. Any questions for me before we get out of here? All right. Overall, also, what I'm seeing on the exams is pretty good. So I'm fairly encouraged by those, but we'll talk a little bit more about those when I have them all graded on Thursday's class. Okay? All right. We'll see you guys Thursday.